And we can also have back-to-back stem and leaves where we can have two sets of data, which we can compare side by side. So we have one in increasing order going to the left and the other set of data increasing order going to the right. And sometimes the key can actually look like this, where this actually represents 41 and this side of the key represents 43. Or just a simple key, 6-1 is 61. Okay, so back-to-back stem and leaves are good for comparing two sets of data. Okay, so let's look at finding the interquartile range from a stem and leaf diagram. So a stem and leaf diagram, bear with me, shows marks out 50 in a maths test. Okay, marks out 50. Okay, does it say how many marks have? Well, anyway, we want to find the median mark, the lower quartile, the upper quartile, and the interquartile range. Okay, so actually this is the stem and leaf diagram. It's done for us already. We've 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 marks, 15 people, 15 sets of data, whatever you want to call it. So what is the median mark? The median mark is the middle mark. So that's the 8th mark. So it's halfway, and the 8th mark is 1, 2, 3, 4, 5, 7, 8, 31. Okay. The lower quartile is in the first quarter. Okay, so if we divide the data, if this is the 8th mark, then we've 1, 2, 3, 4, 5, 6, 7 bits of data that side, 1, 2, 3, 4, 5, 6, 7 that side. So our lower quartiles in the first quarter, it's here. So we've 3 bits of data this side of it and 3 that side. So our lower quartile is 4Q1. And our upper quartile, then, we divide the rest of the data into its 2 sets of 3, and this is the 3/4 mark, that's our Q3. So the upper quartile is actually 41. Okay, sorry, and this one is 24, apologies, it's 2, 4, 24, Q1. So our interquartile range is always our Q3 minus our Q1, that's 41 minus 24, and it's equal to 17. Now just some quick tips on making sure our graphs are never misleading. Always make sure to label both axes, always. As far as possible, start at 0, otherwise that can be misleading to people, and keep columns to equal widths as well. Don't start messing around with column widths. Keep everything the same as much as possible. Now this part of the video is just for senior students only, not for junior cycle students. Okay, so we're going to look at scatter graphs, and scatter graphs are used to compare 2 sets of data to see if a relationship exists between them. Okay, so the strength of the relationship is known as a correlation, and the closer the points in a scatter graph are to a straight line, the stronger the correlation or the relationship between the 2 bits of data would be. Okay, so we might plot a graph and plot some points, and we can see that that's a strong positive correlation. If we've a whole flock of points scattered around, we might have a weak positive correlation, a strong negative because they're mostly hugging a line, and a weak negative is there's many of them around what might be a line. So weak negative, and then there's no correlation, but there's no line to be found, good, bad, or different. Okay, and statisticians have worked out a way of measuring correlation. If you take a look at this here, where they would say that if we have a strong positive correlation like this, where we have a straight line graph, we say R for correlation is equal to 1. Or if we have a strong negative, the strongest negative correlation, R is equal to -1. and all other correlations are between 1 and -1. So this would be r equals 0, and this is quite negatively strong, so it'd be near to -1, say minus 0.8. Okay, and just the notion, we'll do an example in a second now of causal relationships. Okay, so if we think about the age of a car and how it causes a change in the car's price, we could say that there's a causal relationship between the two, the age of the car and the price of the car. But just to note that a positive correlation does not always mean a causal relationship. You could plot a scatter graph of people buying laptops and fridges. So they go into Harvey Norman just to buy a fridge, but they end up spotting a laptop they like, and there might appear to be a strong correlation between people buying laptops and fridges. But that doesn't necessarily mean that if you buy a laptop, it will cause you to buy a fridge. There might not necessarily be a causal relationship there. Okay. So if we were to label this, we could say it's the laptops and the fridges. So more someone buys a laptop, the more likely is they'll buy a fridge. Okay. So let's look at an example here to work out or look at correlation. Okay. The table shows the weights and heights of 12 people. So here's the table. 12 pieces of data there. And we're asked to plot a scatter diagram. Okay, and we simply do that by plotting. Well, first of all, we'll set up our axis. Now, we're not starting at 0, we could, but there's no need to really here. So we start at 140 for our height range up to 180, because we've looked through these and we see that we have a height starting at 150 here. Okay, so that's this one here. So there's our range, 150 to 180. And then we have our weights. Then we're going as far as 70 is the highest one there. So we'll go from 50 to 70. And then we simply plot the points. So we simply plot the points. So we have 150 and 57, out 150, up 57. 152 and 62, out 152 up to 62, and we just plot all the points accordingly, and that is our scatter diagram. Now, what can we say about the correlation? Well, the correlation is weak, as we don't quite have a straight line. They're all bunched around there somewhere. But we can say that overall it's positive, because an increase in height tends to lead to an increase in weight. In other words, the taller the person is, the heavier they appear to be.